Hello, this is Dr. Hanaa Assil, and this is Unit 4 of May-June 2025 in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the first question. This question is about carbonyl compounds. Propanone reacts with hydrogen cyanide in the presence of potassium cyanide. How is this reaction classified? Remember, propanone is a ketone, and aldehydes or ketones can be attacked by cyanide, in which lone pair of electrons on the carbon attack the slightly positive carbon of the carbonyl. This adds the cyanide at the carbonyl carbon to form a cyanohydrin. Now, this is called a nucleophilic addition. Any reagent that has lone pair of electrons that can attack a slightly positive carbon, that is a nucleophile. The cyanide is added, so this is nucleophilic addition. What is the first step in the mechanism of the reaction between propanone and a mixture of HCN and KCN? So again, we said, what is the first step? The first step is the lone pair of electrons on the carbon. Notice that it is on the carbon, not on the nitrogen. The lone pair of electrons are on the carbon and they attack the carbonyl carbon, which is slightly positive. So this is actually the correct answer. What is the name of the organic product formed in part A? Okay, this is the product formed. If we have propanone, we were told that we're starting with propanone. We add cyanide and we form a cyanohydrin. Now that product is called the cyanohydrin, but how do we name it? Well, this is the chain. It has 3 carbons, so this is actually called, and the 3 carbons, remember, you count the carbon of the nitrile or the cyanide. So this is actually propane nitrile, and then we have the substituents are 2-hydroxy 2-methyl propane nitrile. Remember, the CN as a reagent is called the cyanide. In the compound, you can name it as something nitrile, count the carbons including the carbon of the CN. Which of these carbonyl compounds would produce pale yellow crystals when warmed with iodine in the presence of sodium hydroxide? Remember that iodine in presence of aqueous sodium hydroxide, this is the iodoform test that forms a yellow precipitate if we start with something that has a carbonyl next to a methyl group. So the question is, which of these has a carbonyl next to a methyl group? So butanone, this is butanone, and this does have the methyl C double bond O part that would react to give the triiodomethane. So this is actually the compound that will give a pale yellow crystals. Butanal does not have this group. Pentane 3-one does not have this group. The carbonyl is not next to a methyl. And 2-methyl propanal also does not have the required group. What is the formula of the pale yellow crystals formed? Remember the iodoform test with aqueous iodine. This will remove the methyl group that's next to the carbonyl and form triiodomethane. Remember, the other product would be the sodium salt of the rest of the compound, and that gives an antiseptic smell. Which of these statements about the reaction of ethanoyl chloride with ammonia is not correct? Again, please pay attention. Are we required to get what is correct or what is not correct? So here we're reacting ethanoyl chloride with ammonia. This is ethanoyl chloride and ammonia. Remember, the ammonia attacks the carbonyl and replaces the Cl. The product formed is an amide. So when we are told an amide is formed, that is correct, because that compound formed is an amide. The reaction is exothermic. Misty fumes and white smoke are formed. This is correct because the other product is hydrogen chloride gas, and hydrogen chloride gas is observed as misty fumes. A gas is produced that turns damp red litmus paper to blue. Of course, this is the wrong statement because what is formed is HCl. HCl is an acid. So if tested with damp red litmus paper, hydrogen chloride as a gas, of course, is not an acid, but when it dissolves in the water on damp red litmus paper, it turns the litmus paper from blue to red, not red to blue. Which of these substances would be expected to have the greatest standard molar entropy? When do we have higher entropy? Remember, when comparing between solids, liquids, and gases, remember that a solid has, as we go from solids to liquid to gases, there is more randomness, increase in disorder, so increase in entropy. So gases are higher entropy than liquids, and liquids higher than solids. But here we're comparing between solids. All of them are solids, so the more complex would have higher entropy. More complex means more atoms, more electrons in the molecule. That would be more or higher entropy. What is the pH of a 1.25 mole per decimeter cubed solution of hydrochloric acid? We know that hydrochloric acid is a strong acid, so the concentration of H+ ions is the same as the concentration of the solution. All the molecules ionize. And that means we can get pH by minus log of the concentration of H+ ions, and this gives this number. At 25 degrees Celsius, the pH of pure water is 7, and at 75 degrees Celsius, the pH is 6.4. Why is the pH of pure water lower at 75 degrees Celsius than at 25? Okay, let's take a look at the choices. There are more hydrogen ions than hydroxide ions when water is at 75. You should know that that is wrong. In water, the concentration of H+ ions is always equal to concentration of OH-, and that is why we always say water is neutral even if its pH is lower than 7. So A is wrong. The dissociation of water is endothermic, so concentration of hydrogen ions is lower at 75. When we say that at 75 the pH is 6.4, that means, remember, when pH is lower, that means we have higher concentration of H+ ions. So when they say the concentration of hydrogen ions is lower, no, that's not right, because the pH is lower. That means more H+. The dissociation of water is endothermic, so the concentration of hydrogen ions is higher at 75. This is correct. Now, when we say that water dissociates to give H plus ions, and at higher temperature, I have more H plus, that means at higher temperature, this equilibrium shifts to the right to give more H plus ions, and that means that the forward reaction is endothermic. If we increase temperature and it goes to that side, then that side is endothermic, and the concentration of hydrogen ions is higher at the higher temperature. Dissociation of water is exo? No, it is not. It should be endo, since at higher temperature I have more H plus ions. A sodium hydroxide solution with pH 12 is diluted by a factor of 100. What is the pH of the diluted solution? So if we have pH 12, that means the concentration of H plus ions is 10 to the minus of the pH. Now, if we dilute that 100 times, that means the concentration now is 10 to the minus 10, so the pH minus log of that is 10. High-resolution mass spectrometers can give peak data accurate to 4 decimal places. An organic compound X has molecular ion peak at m/z 60.0210. Remember, that means that that is the exact MR, or molecular mass, of that compound. The accurate relative atomic masses are shown. Which compound is X? So basically, we're just calculating the MR using these exact numbers and determine which of these is 60.02. So, molecular mass of this first one, of course, the masses of each one that is given to these 4 decimal places times the number of atoms we have. The MR of that second one is the one that comes out to 60.021. All the others have the wrong molecular masses. A thin layer chromatogram of a substance is shown. What is the RF value of the sample? Remember, first of all, RF value is the distance moved by the spot over the distance moved by the solvent. So, if we were to measure it, it is the distance from, remember, it's from the baseline, not from the bottom of the paper. From the baseline where the sample was placed to the position of the sample, divided by from the baseline to the point where the solvent went, which we call the solvent front. But even without actually measuring this with a ruler, of course we can measure this with a ruler, but without even measuring it with a ruler, obviously the spot is about 3/4 of the way up, so it is 0.73. That would be the correct choice. It's not, remember that RF values can never be more than 1, so D is totally wrong. 0.27 would be way near to the baseline, just 1/4 of the way up. 0.69 would be lower than that point, so just by estimation it is 0.73. If not, use a ruler and calculate it. In an experiment to determine the rate of reaction between bromine and methanoic acid, which method would not be suitable? Remember, when we try to measure the rate, how can we measure it? Now, our first choice here is quenching and titrating with an acid. Now, this is something that gives an acid. So if we're going to titrate, we should titrate with a base, not with an acid. So this one is not suitable. Measuring the loss in mass, yes, we could use that because the reaction gives out a gas, so there will be a loss in mass, and we can measure the mass every minute. Colorimetry, yes, we can use colorimetry because we have bromine changing to bromide. Remember that bromine originally is reddish brown or orange, and as the reaction proceeds, the color disappears. So this can be measured by colorimetry, in which we pass light through it, and the difference, the change, the gradual change in the color can be determined. Measuring the volume of gas produced, yes, we have carbon dioxide gas being produced, so we can have a gas syringe and measure the volume every minute. The reaction shown is second order with respect to NO and first order with respect to oxygen. If the concentration of NO is doubled and the concentration of O2 is tripled, by what factor will the rate increase? We are told that it is second order with respect to NO, first order with respect to oxygen. If concentration of NO is doubled, concentration of oxygen is tripled, so that is 3 times 4, so that would be 12 times in which the rate increases. A chloroalkane undergoes hydrolysis according to the equation shown. The rate equation is dependent only on the concentration of the halogenoalkane. So which chloroalkane is most likely to be this compound? Remember we said when we have alkaline hydrolysis of a halogenoalkane, either we have a primary halogenoalkane in which the hydroxide ions attack at the same time that the halogen leaves. So bromine or chlorine leaves at the same time that the OH is attacking, and that means both of them are involved in the slow step of the reaction, and the rate equation involves concentration of both reactants. But this is if we have a primary halogenoalkane, and this is SN2. But if we have a tertiary halogenoalkane, we said the Br leaves first in the slow step to form a carbocation, then the hydroxide attacks. So the rate equation depends only on the concentration of the halogenoalkane. So if we have this, according to what we are told, this reaction is SN1, in which the rate depends only on the concentration of the halogenoalkane. So actually we're looking for which of these is a tertiary halogenoalkane. So let's take a look. The one in A is a primary. Now the choice in B, this is a tertiary, so this would react in SN1 and the rate would depend only on the concentration of the halogenoalkane. Now the others are not tertiary, this is a secondary and this is a primary, so the answer is B. This question is about the titration curves obtained by reacting different acids and alkalis of the same concentration. Which curve is produced by adding ammonia to hydrochloric acid? So we're starting with hydrochloric acid. That means we're starting with a very low pH. So actually my choice would be either curve 1 or curve 3. Remember 2 and 4 are starting with very high pH. So these would be incorrect. So we're starting with HCl, so we need to start with a pH of about 1. So that's curve 1 or 3. And then we're adding ammonia. Ammonia is a weak base, and you should realize that at the end, our pH cannot be higher than 10 or 11. It cannot go up to 14. So obviously, curve 3 is the correct curve that would be obtained when adding a weak base to a strong acid. Which of these indicators would be most suitable to determine the endpoint of the titration that gives curve 4? So, to determine which indicator is suitable, we look at the equivalence point in the curve, which is the midpoint in that sharp decrease in pH. So, obviously, the equivalence point here is somewhere around 8 to 9 or below 10. So, which indicator has this kind of pH range? Obviously, it is thymol blue. This equation is about the equilibrium for the reaction shown, which is the expression for the equilibrium constants Kp. Remember that to write the expression for Kp, it is the partial pressure of products raised to the power of their coefficients divided by the partial pressure of the reactants raised to the power of their coefficients. So obviously this is the correct answer. Which statement about this equilibrium is correct? Well, let's see. This is the equilibrium that we have. Now, the first choice says increasing the pressure increases the value of Kp. Again, please remember the value of the equilibrium constant will not change unless if we change temperature. The only factor that changes the value of the equilibrium constants is temperature. So when we say increasing the pressure increases Kp, that is wrong. Decreasing the pressure decreases the yield of SO3. Well, let's see. Remember that decreasing the pressure will cause the equilibrium to shift to the side with higher number of moles. Decreasing pressure goes higher number of moles, and the opposite is correct. So here we're decreasing the pressure, so this means that this reaction will go to the side with higher number of moles. That means the equilibrium will shift to the left, and that would give us less SO3. So this is correct. It would decrease the yield of SO3. Adding a catalyst increases the yield. Remember, adding a catalyst. The catalyst, first of all, speeds up both forward and backward reactions. So it does not have any effect on point of equilibrium. So it would not cause the equilibrium to move forward or backward more. And it will have no effect, of course, on the value of Kp or the yield of the product. What is the relationship between equilibrium constants K and delta S total? Remember, this is the relationship. Delta S total is equal to R ln K, natural log of K. Question 14 says, this question is about nitrosyl chloride, which is a yellow gas. Nitrosyl chloride decomposes into yellow-green chlorine gas and colorless nitric oxide as shown. A mixture of nitrosyl chloride, chlorine, and nitric oxide was placed in a sealed container and allowed to reach equilibrium. Explain what you would expect to see. So, observation. When the pressure of the equilibrium is increased. Okay, so we have this equilibrium, and we are told that originally the NOCl is a yellow gas. The chlorine gas, of course, we know is a yellow-green gas. Now, we are doing what? We are increasing pressure. Again, increasing pressure shifts the equilibrium to the side with less number of moles. So increasing pressure means that that equilibrium will move to the left, and that means the mixture will become more yellow, since increase in pressure shifts the point of equilibrium to the left to give less number of moles. 0.25 mole of nitrosyl chloride in 500 centimeter cubed seal container was heated to 200 degrees Celsius. At equilibrium, there was 0.016 mole of chlorine in the mixture. First of all, write the expression for the equilibrium constant. Again, the expression here, we need Kc, so we're talking about concentrations. And remember that concentrations are indicated by these square brackets. The square brackets indicate concentration. And Kc would be concentration of the products raised to the power of their coefficients divided by concentration of reactants raised to the power of their coefficient. Complete the table using the equilibrium equation and the data. So this was the equation, and we are required to get number of moles at equilibrium, concentration at equilibrium. So that means we need to go through an ice chart. Initially, we are told that we're starting with 0.25 of NaCl and 0 of the other gases. Now, in any equilibrium, the change is the reactants will lose 2 times X, which X is the amount that we don't know yet, and the products will have plus, or we will form 2X and X using the coefficients. Now, that means at equilibrium, we're left with the rest of whatever we started with. And then we're told that at equilibrium, we have 0.016 of chlorine. That means that X is 0.016. Now, put that into each of these. That means at equilibrium, I have the rest of the 0.25 of NaCl and the 2X, because the coefficient of NO is 2, so 2 times 0.016 and the 0.016 of the chlorine. So these are the equilibrium number of moles, and then we need to get the concentration. Now, we were told that the volume is 500 centimeter cubed, or that means 0.5 decimeter cubed. We divide by 1,000, of course. And that means the concentration of each of these would be the number of moles divided by the volume. If we do that, we find that these are the concentrations of each of the gases at equilibrium. Using your answers from B1 and B2, calculate the equilibrium constants, give your answer to an appropriate number of significant figures, and include units. So what did we calculate? We know that this is the expression for Kc, and this is what we calculated. So we just put the numbers into the expression to get this value. Now we need units. Please don't forget to put in units. Remember, each concentration is mole per decimeter cubed. So something to the power 2 would be mole to the power 2 over decimeter to the power 6. And any normal concentration is mole over decimeter cubed. Cancel whatever is the same, and the units come out to mole per decimeter cubed. When the temperature is reduced, the value of the equilibrium constant Kc becomes smaller. Explain what can be deduced about the nature of the reaction. Remember, if this is the reaction and the value of Kc becomes smaller, first of all, that means we have less products, and that means the reaction or the point of equilibrium shifts to the left. So if it goes backward when temperature is decreased, that means that backward is exo, and that means the forward is endothermic, so that decrease in temperature shifts the equilibrium to the left, which is exothermic. This question is about butanoic acid. Some reactions involving butanoic acid are shown. Identify the reagent by name or formula and the conditions required to carry out reaction A. So where is reaction A? This is reaction A, in which we're changing what? Please pay attention to the direction of the arrow. We're changing acid to alcohol. So how do we reduce an acid to an alcohol? Of course, we use lithium aluminum hydride in dry ether. This would change the acid to aldehyde and then to a primary alcohol. Name the type of reaction taking place in reaction B. Now, which one was reaction B? This was changing the cyanide to, or the nitrile to an acid. And that means we're adding aqueous acid. This is called hydrolysis. So to change a nitrile to an acid, we add aqueous HCl, for example. That gives the acid, and that is hydrolysis. Give the structural formula and name of substance C. Now, what was substance C? That was something obtained from acid reacting with an alcohol in presence of sulfuric acid as a catalyst. Of course, this is esterification, in which we have the acid reacting with the alcohol. So this is our ester. Now, what is the name of this ester? Remember, we start with the name of the alcohol. So methanol. So this is methyl and butanoic acid. So this is methyl butanoate. Identify by name or formula the reagent required to carry out reaction D. Where was reaction D? This was changing the acid to an acyl chloride. So we're reacting the acid with what? With PCl5, and this gives HCl gas in the form of white, steamy white fumes. So the reagent is phosphorus pentachloride, and the observation is steamy fumes of hydrogen chloride gas. Write the full equation for the formation of substance E. So what was substance E? This was reaction of the acid with sodium hydrogen carbonate. So of course, acid plus sodium hydrogen carbonate gives the sodium salt. So you just remove the H of the acid and replace it with an Na, plus carbon dioxide plus water. Make sure that it is balanced. Butanoic acid is very soluble in water. This is due to strong intermolecular forces between butanoic acid and water molecules. Complete the diagram by adding one water molecule. To show this intermolecular force, include relevant dipoles and lone pairs and label the intermolecular force involved. Of course, if we have acid and water, these can form what? These can form hydrogen bonding. So actually there are several ways of drawing the hydrogen bonding with the acid. This is one of them, in which the hydrogen of the OH is attracted to the slightly negative oxygen of the water. Remember that the lone pair of electrons on the oxygen form what we call a hydrogen bond. The oxygens are slightly negative and the hydrogen is slightly positive. And remember that this bond is at an angle of 180 around the hydrogen. So this OHO should be on the same line. The angle is 180. Proton NMR spectroscopy and mass spectrometry give detailed information about the structure of organic compounds. Discuss the similarities and differences in the spectra for propanal and propanone. Include in your answer proton NMR spectroscopy, the number of peaks, relative peak areas, splitting patterns. For mass spectrometry, any M over Z peaks that show one similarity and one difference between the spectra of the two compounds. So what are we comparing? We're comparing propanal to propanone. So let's first talk about the proton NMR spectroscopy. Of course, in the propanal, we will have 3 proton environments, so 3 peaks with relative area 1 to 2 to 3. We have the hydrogen of the aldehyde, the CHO. This is for peak area 1, but it is a triplet because on the neighboring carbon we have 2 hydrogens. Remember, we follow n+1 rule, so 2 hydrogens means the peak will be split into 3, so this is a triplet. Then the CH2 has 3 protons on the carbon on the left and 1 proton on the carbon on the right, so that's 4 hydrogens on neighboring carbons, so that would be a quintet. And the peak for the CH3s will be a triplet because it has 2 protons on the neighboring carbon. Now the propanone, you can see that the propanone is symmetrical, so both methyl groups are equivalent. So actually we will have only 1 peak, which is a singlet. There is no protons on the neighboring carbons for each of them, and peak area will be for 6 protons. Now we still need to talk about the mass spectrometry. So what is the similarity or the difference, both actually, of propanal and propanone? Remember that you need to calculate the MR of each. Now the MR of both is 58, and both of them have a methyl group that will give a peak at M over Z, 15 for the fragment of CH3+, but they will be different in what? The propanal will have a peak at 29, while the propanone will have a peak at 43 for these 2 different fragments. Please remember that when you write the fragments, they are positive ions, so you must have a positive for each fragment. Question 17 says, this question is about weak acids. The values for the acid dissociation constants of ethanoic acid and chloroethanoic acid are shown. Write the expression for Ka for ethanoic acid. Ethanoic acid is a weak acid, so it will dissociate to give this, and the Ka is the concentration of products over the concentration of the acid. Calculate the pH of 0.25 mole per decimeter cubed solution of ethanoic acid. Remember again, to get the pH of a weak acid, we use this equation. Concentration of H plus ions is the square root of Ka times the concentration of the acid. So using that equation, the concentration of H plus will come to this number, and the pH is minus log of that, so the pH is 2.69. State one assumption you have made when calculating the pH of a weak acid. Again, remember the assumptions that we make when we calculate the pH of a weak acid is the dissociation of the weak acid is negligible, so we regard the concentration of the acid at equilibrium to be about the same as the initial concentration. And the fact that the concentration of H plus from the dissociation of water, this is regarded as negligible, so that the concentration of H plus formed is only due to the dissociation of the acid. These are the 2 assumptions made when calculating the pH of a weak acid. So just a reason why chloroethanoic acid is a stronger acid. Remember, If we're given Ka, remember that the higher Ka is more acidic. So ethanoic has 1.7 times 10 minus 5. Chloro is 1.3 times 10 minus 3. So having a chloro compound is more acidic, and that is because chlorine is electron withdrawing. This weakens the OH bond, causing the H plus to be lost easily. Remember again, if we have a chlorine in the molecule, the nearer the chlorine is to the acid, the stronger the acid, because the chlorine is electron withdrawing. As it moves further down the chain, it has less effect, so less acidic. Also, if we have more chlorines, this is more acidic. So having one substituent as a chlorine, or 2 or 3, this increases the acidity. And remember that if we have different halogens, the one that is more electronegative would cause the acid to be more acidic. So an acid having fluorine is more acidic than the one with chlorine, and so on. So please remember all of these. When ethanoic acid and chloroethanoic acid are added together, an equilibrium is set up containing two acid-base pairs. So both of them reacting together, that means one of them has to act as an acid proton donor. The other one will have to act as a base and accept the proton. So when we have both of them, the one that is more acidic means higher Ka, is the one that loses the proton. So higher Ka, more acidic, that is the one that will lose the proton. So we said the chloro is more acidic, so that is the one that will act as acid 1, and it loses the proton to form a base. So that's base 1. The other one, which is the ethanoic acid, would then need to act as a base, so that is B2. It takes the proton and becomes an acid, so that is A2. Remember, the acid becomes conjugate base, the base becomes conjugate acid. A buffer was made by mixing 8.2 grams of sodium ethanoate with 250 centimeter cubed of 0.7 mole per decimeter cubed solution of ethanoic acid. Calculate the pH of the buffer. Again, we're going to say the pH of the buffer is what? The pH is pKa plus log of the ethanoate over concentration of the acid. So we need number of moles of the ethanoate because we have only mass. So mass over the molecular mass of sodium ethanoate, that gives the number of moles of the ethanoate. We need its concentration. Concentration is number of moles over the volume, and the total volume is 250. So that is 0.4, that is mole per decimeter cubed concentration of A minus. The concentration of the acid, we have concentration times volume, so that is the concentration of HA. Put that into the equation. Remember that pKa is minus log of the Ka that we're given, plus log of the concentrations we calculated. This comes out to a pH of 4.5265. A type of bubble bath contains a weak acid and the indicator bromocresol green. The bubble bath is initially yellow, but when diluted with bath water, its color changes from yellow to green to blue. Use the information on this page of the data booklet to deduce why the bubble bath changes color. So when you look at the data booklet, you will find this about bromocresol green. So we are told that in acid it's yellow, in alkaline it is blue, And we should realize that going from yellow to blue, we have to go through green, and that's actually why it's called bromocrystal green. And what is happening is we had the bubble bath originally a weak acid. So a weak acid containing bromocrystal green would be yellow. And then we're told that the bubble is initially yellow, but when diluted with bath water, its color changes from yellow to green to blue. So that means the weak acid in the bubble bath, we had low pH, so we started with the low pH color for the bromocrystal green, which is yellow. But as we add the bath water, as we add water to it, the pH rises. It goes towards the pH of the water. So the indicator is changing color because the pH is rising from the low pH to the higher pH, and we see that the color will change from yellow to green to blue. Question 18 says, this question is about the kinetics of the catalytic decomposition of hydrogen peroxide using manganese oxide as a catalyst. So we have hydrogen peroxide, we added, so in an experiment, 10 centimeter cubed of hydrogen peroxide solution was added to 150 centimeter cubed of water. A small amount of manganese oxide, and we're told this is the catalyst, was added and the clock started. Every 5 minutes, 10 centimeter cubed samples of the reaction mixture were withdrawn using a pipette and transferred to a conical flask. The samples were then acidified with dilute sulfuric acid, titrated with potassium manganate, and the equation for the titration is shown. The results of the experiments are given in the table. And the first question is, the reaction in the sample stops immediately on removal from the reaction mixture. Remember that the hydrogen peroxide needs the manganese dioxide in order to react. So once we remove the sample, the manganese dioxide is a solid. So the solution no longer has the catalyst, so the reaction stops. State why it is not necessary to calculate the concentration of hydrogen peroxide solution when trying to deduce the order of reaction with respect to hydrogen peroxide. Remember, we are titrating with potassium permanganate, and the volume of the potassium permanganate needed is directly proportional to the amount of H2O2 present. So we can use these results directly to determine the order of the reaction. And this is because the concentration of hydrogen peroxide is directly proportional to the volume of the manganate used. Plot a graph of the volume of potassium manganate solution against time. So we have the time in minutes on the x-axis, the volume of manganate in centimeter cubed on the y-axis. Distribute the numbers so that you use as much of the graph paper as possible and plot the points, then join them with smooth curve. Use your graph to show that the reaction is first order with respect to hydrogen peroxide. You must show you're working on the graph. So this was the graph, and in order to determine if it is first order or not, remember that we said the volume of manganate is actually just like concentration of hydrogen peroxide. So this is a graph of concentration of hydrogen peroxide versus time. And if we calculate the half-life, if it is first order, the half-life should be constant. So calculating the half-life of this, we start from, for example, 32.5, 16 point something. This takes 12 minutes, starting from 20 to 10. Again, this takes 12 minutes, so the half-lives are constant, and that means it is first order. Two possible mechanisms have been suggested by students carrying out this reaction. So the reaction, remember that this was the reaction and we were trying to determine the order, and we said it should be first order. So explain whether or not these mechanisms are consistent with the reaction being first order. Remember, when you look at mechanisms, we're looking at the slow step or anything before it, if there is anything before it. So the slow steps here, this is what we're looking at. If we need it first order, that means we need the H2O2 to be just one molecule or 1 mole in the slow step. Mechanism 1 obviously is wrong, because according to mechanism 1, the slow step has 2 molecules of H2O2, and that means it should be second order, not first order. So the mechanism 2, that's the one that's correct, because the slow step involves only 1 molecule of H2O2. So mechanism 2 is correct. The slow step involves only 1 molecule or 1 mole of hydrogen peroxide, so that is first order. While the slow step in mechanism 1 indicates that the reaction is second order, since it involves 2 molecules of hydrogen peroxide. This question is about copper compounds. Crystals of hydrated copper sulfate lose water when heated, forming anhydrous copper sulfate. Using the data in the table, so we're given standard enthalpy of formation of each of the reactants and product and the standard molar entropy. Using the data, calculate the standard enthalpy change of this reaction for this reaction. Okay, so remember, according to Hess's law, if we're given standard enthalpy of formation of each, that means we're forming from elements, and that means the delta H for that reaction would be the formation of products minus the formation of the reactants. So be careful with the sign. Already the formation of products are in negative or negative values, minus of a negative value for the reactant. The overall delta H is a positive value. Using the data in the table, calculate the standard molar entropy change for this reaction. Again, the entropy change here is the entropy of the products minus the entropy of reactants, and we put in the numbers given. Please take into account coefficients. Remember, we have 5 water, so you multiply by 5 for the water. The overall is plus 158. Remember that all of these are in joules, so this is joule per degree per mole. Using your answers, calculate the lowest temperature at which hydrated copper sulfate will decompose. Remember, lowest temperature is when the delta S total is 0. That is when the reaction becomes feasible. We already have the delta H, we have the delta S system, we got it in joules, so divide by 1000 to get it in kilojoules. We know that delta S total is delta S system plus delta S surroundings. Delta S surroundings is minus delta H over T, and the lowest temperature would be when the delta S total is equal to 0. So that means the delta S system is equal to delta H over T, and therefore the T is the delta H over the delta S system. Divide these numbers, you get the temperature, of course, in Kelvin. If you want it in degrees Celsius, subtract 273. Hydrated copper sulfate is soluble in water. A student carried out an experiment to determine its enthalpy change of solution. 100 grams of distilled water was placed in a polystyrene cup. The temperature recorded. 21.36 grams of hydrated copper sulfate was added to the distilled water. The mixture stirred and the minimum temperature recorded. Using this data, the students calculated enthalpy change of solution was plus 12.3. So this is our delta H of solution. Calculate the temperature change in this experiment. We are given specific heat capacity of the solution. Notice that it is 3.7. The total mass of the solution, we are told that we put 100 grams of distilled water, but then we're told that the total mass of solution is 121.36, and we're given the MR of the hydrated salt. We know that delta H is Q over N, and the Q is MC delta T. So what we have is the delta H is MC delta T over N. So if I can get N, so the N would be the number of moles of the hydrated copper sulfate. We have 21.36 grams. So the number of moles is the mass over the molecular mass given. That is the number of moles. The mass of the solution is given, total mass of solution 121.36. The C is given as 3.7. The delta H is given as 12.3. Put in all these numbers, but notice, please, that the specific heat capacity is in joules. So the delta H is given 12.3 kilojoules. You need to multiply that by 1,000. All of these would be in joules, so that the delta T comes out to 2.3. Copper chloride is another copper compound that is soluble in water. It is possible to calculate the enthalpy change of solution using a Hess cycle and the lattice energy and the enthalpy changes of hydration. First of all, explain what is meant by enthalpy change of hydration. Remember, enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. So basically, we have gaseous ions forming an aqueous solution. That the delta H for that would be the delta H of hydration. Complete the Hess cycle. So we have the aqueous ions already put for us. That means to get delta H of hydration, we start with the gaseous ions. The lattice energy would be changing the gaseous ions to what? To the solid ionic compound. Complete the expression for the enthalpy change of solution using the enthalpy changes of hydration and lattice energy. So if we have this, we want delta H of solution. Please follow the direction of the arrows. This means that lattice energy plus delta H of solution is equal to the sum of the delta H hydration. And that means delta H solution is the delta H hydration minus the delta H lattice. The lattice energies of copper chloride is minus 2811 kilojoule per mole. Use this value, the data in the table, and your expression in C3 to calculate the enthalpy change of solution. So we already said we have this, and we already said that the delta H of solution is actually the sum of the delta H hydration minus the lattice energy. We are given the values for enthalpy change of hydration of copper. Remember that we have 1 copper ion and 2 chloride ions, so you need to multiply the value for the chloride by 2, minus lattice energy, which is already a negative value, so minus of a negative value, that would be positive, and the overall answer would be minus 45 kilojoule per mole. The enthalpy change of hydration of copper plus 1 is minus 593 kilojoule per mole. Remember that when we calculated, or when we're given for the copper 2 plus, it was given minus 2100. So this is much higher. The copper 2 plus is higher than the copper plus 1. Explain why the hydration enthalpy of copper plus 1 is much less endothermic than copper 2 plus. Well, remember that the higher the charge, we're talking about hydration, and hydration means the interaction between the ions and the water. And the stronger the interaction, the more exothermic the delta H of hydration. So the copper plus 1 is less exothermic because it has a lower charge density than the copper 2 plus, so weaker electrostatic forces of attraction with the water, so less energy is released when the ions are hydrated. And that's the end of the paper. I hope this was useful to you. Thank you for listening.